Hello students, welcome all of you to the YouTube channel Physics Quantum Classes. In this video, we will discuss a very important topic in thermodynamics, which is Maxwell's four thermodynamical relations for B.Sc Part 1 Physics, all courses, in lecture number 9 of thermodynamics. To derive Maxwell's four thermodynamical relations, we have to start from the first law of thermodynamics, which in differential form is given by dq, which is the amount of heat supplied to a system. dq equals to du plus dw, where du is the increase in internal energy of the system and dw is the work done by the system. जब किसी सिस्टम को बाहर से dq अमाउंट का हीट सप्लाई किया जाता है तो उस अमाउंट ऑफ हीट का कुछ पार्ट उस सिस्टम का इंटरनल एनर्जी को इंक्रीज करने में, बढ़ाने में यूज होता है, जो कि du है. सो du इज द इंक्रीज इन इंटरनल एनर्जी ऑफ द सिस्टम एंड रिमेनिंग पार्ट ऑफ हीट dq वह कांस्टेंट प्रेशर पर उस सिस्टम का वॉल्यूम dv से इंक्रीज करने में वर्क डन में यूटिलाइज होता है. सो du इज द वर्क डन बाय द सिस्टम at constant pressure to increase the volume of the system through dV. So we can further write first law of thermodynamics is dq equals to du plus dw, and in place of the dw we can write p into dV, that is work done by the system to increase the volume of the system through dV at constant pressure. So we have to write in place of dw p into dV. So it is dq equals to du plus dw is p multiplied by dv, and say it is equation number 1. Therefore, increase in internal energy of the system du equals to dw minus p dv. Now using second law of thermodynamics in mathematical form, which is change in entropy ds equals to amount of heat supplied to the system, that is dq, upon absolute temperature capital T, that is ds equals to dq upon capital T, and this is the mathematical form of second law of thermodynamics. So amount of heat supplied to the system dq equals to T multiplied by ds. So in place of dq we can write T into T multiplied by ds minus p dv, and say it is equation number 2, where dq equals to product of absolute temperature capital T and increase in entropy ds, from that is from the mathematical form of second law of thermodynamics. Now suppose internal energy capital U, symbol of internal energy is capital U, symbol of entropy is S, and symbol of volume is volume of the system is capital V. Suppose internal energy U, entropy S, and volume of the system be the functions of two variables, say x, a small x, and a small y. So we can write U, that is U is the function of two variables x and y. Entropy S is also the function of x and y, and volume of the system V is also the function of two variables x and y. Therefore we can write U as the perfect differential, that is increase in internal energy or change in internal energy of the system du equals to del u partial differentiation del u upon del x at constant y. तो y को ब्रैकेट देकर सफिक्स में लिखना होगा. सो del u upon del x at constant y into dx plus del, now in second term del u upon del y at constant x multiplied by dy. So change in internal energy du equals to del u upon del x at constant y into dx plus del u upon del y at constant x into dy. Because we have assumed that internal energy capital U is the function of two variables, say a small x and a small y. Similarly, we have also assumed that entropy S and volume V of the system are also the functions of two variables x and y. So change in entropy or increase in entropy ds can be written as del s partial differentiation del s upon del x at constant x at constant y, del x, that is change in entropy with respect to x, del x upon del s upon del x, keeping y constant. So y is constant. So del s upon del x at constant y into multiplied by ds plus del s upon del y partial differentiation again, that is differentiating entropy s partially with respect to y. We have change in entropy s with respect to y is del s upon del y at, but keeping the first variable x constant, at constant x del s upon del y at constant x multiplied by into dy. And for volume v, change or increase in volume v can be written in the perfect differential form, as dv equals to del v upon del x at constant y into dx plus del v upon del y at constant x into dy. So we have obtained du, ds and dv, that is increase in internal energy du, increase in entropy ds or change in entropy ds, and increase or change in volume dv in differential form, and say it is all three together is equation number 3. Say all three relations du, ds and dv, we have assumed all three equations as equation number 3. Now substituting for du, ds and dv in both sides of equation 2, which we have obtained from the first law of thermodynamics, that is increase in internal energy du equals to tds minus pdv. So using equations 3 in 2, we have using equations 3 in equation 2, we have, in place of du we can write in LHS of equation 2 del u upon del x at constant y into dx plus del u upon del y at constant x multiplied by dy, and it is LHS of equation. Now it is LHS of equation 2. In place of du we have written del u upon del x at constant y into dx plus second term is del u upon del y at constant x into dy. Now RHS is t multiplied by in place of t multiplied by ds. So in place of ds we can write del s upon del x at constant y into dx plus del s upon del y at constant x into dy. So it is tds. In place of ds we have written del s upon del x at constant y into dx plus del s upon del y at constant x into dy. In in the first term of RHS, that is in place of ds in equation 2, and second term is minus p dv. So we can write in place of dv from the third equation of equation 3, that is dv is equal to del v upon del x at constant y into dx plus del v upon del y at constant x into dy. So second term in RHS is now minus p, and now substituting for dv का वैल्यू हम यूज कर सकते हैं del v अंडर ब्रैकेट del v अपॉन del x at constant y into dx, and second term is plus inside the bracket second term is del v upon del y at constant x multiplied by dy. Now bracket is closed. So second term of equation 2 becomes p multiplied by in place of dv we have written del v upon del x at constant y into dx plus del v upon del y at constant x into dy, and suppose it is equation number 4. Now equating the coefficients of dx and dy in both sides of equation 4, we have now write down now equating the coefficients of dx and dy in both sides of equation 4, which is the last equation we have obtained. So we have in LHS we have coefficient of dx is del u upon del x at constant y. So in LHS we can write del u or del u upon del x at constant y, and it is equal to, in RHS coefficient of dx is in the first term, in the first bracket it is t into delta s upon delta x at constant y. So t into t multiplied by del s upon del y, del s upon del x, del s upon del x at constant y, which is the coefficient of dx in the first term of RHS, and another term in the second bracket is that is coefficient of dx is p multiplied by dv upon del v upon del x into at constant y. So second term is that is coefficient of dx in the second term or inside the second bracket of RHS is minus p multiplied by del v upon del x at constant y. So after equating the coefficients of dx in both sides of equation 4, we have obtained in LHS del u upon del x at constant y equals to capital T multiplied by del s upon del s, that is change in entropy partially with respect to x, del s upon del s upon del x at constant y, and second term is that is coefficient of dx in the second term of RHS of equation 2 is minus p into del v upon del x at constant y, and suppose it is equation number 5. And now equating the coefficients of dy in both sides of equation 4, in LHS coefficient of dy is del u upon del y at constant x. LHS में dy का coefficient है del u upon del y at x, and we have del u upon del y at constant x multiply constant x, and this will equal to, now equating the coefficients of dy in RHS of इक्वेशन 4. अब RHS इक्वेशन 4 के RHS में dy के कोफिशिएंट को इक्वेट करेंगे और वह LHS में dy के कोफिशिएंट के इक्वल होगा, क्योंकि हम इक्वेशन 4 के बोथ साइड्स में, दोनों साइड्स में LHS एंड RHS में dx एंड dy के कोफिशिएंट्स को इक्वेट कर रहे हैं. सो इन RHS वी कैन राइट कोफिशिएंट ऑफ dy in first term of RHS of equation 4 is capital T multiplied by del S upon del y. So at constant x, so we can write T multiplied by del S upon del y at constant x, and this is the coefficient of, that is capital T multiplied by del S upon del y at constant x is the coefficient of dy in RHS, in the first term of RHS of equation 4. इक्वेशन 4 के RHS में dy फर्स्ट टर्म में dy का कोफिशिएंट है t मल्टीप्लाइड बाई डेल s अपॉन डेल y इंटू एट कॉन्स्टेंट x, एंड इन सेकेंड टर्म द कोफिशिएंट ऑफ, इन सेकेंड टर्म ऑफ RHS ऑफ इक्वेशन 4 कोफिशिएंट ऑफ dy इज p मल्टीप्लाइड बाई डेल v अपॉन डेल y एट कॉन्स्टेंट x. सो वी हैव माइनस प्लस माइनस माइनस, आगे चूंकि माइनस है ब्रैकेट के बाहर और सेकेंड ब्रैकेट के अंदर प्लस है, तो ब्रैकेट हटाने पर प्लस माइनस माइनस हो जाएगा, इसलिए सेकेंड टर्म दैट इज डी वाई का कोफिशिएंट, सेकेंड जो टर्म है वह निगेटिव होगा. सो इट इज माइनस पी इंटू माइनस पी मल्टीप्लाइड बाई डेल वी अपॉन डेल वाई एट कॉन्स्टेंट एक्स, एंड से इट इज इक्वेशन नंबर 6. It is equation number 6. Now we have to differentiate equation 5 partially with respect to y and equation 6 partially with respect to x. So first of all, differentiating equation 5 partially with respect to y. So differentiating equation 5 partially with respect to y, we have in LHS we have del upon del y of del u upon del x at constant y. So we have del upon del y of del u upon del x is del square u upon del y into del x, and in RHS of equation 5 the first term is t multiplied by del s upon del x at constant y. So differentiating t with respect to y, we have del t upon del y. We have to differentiate equation 5 both sides with respect to y. इक्वेशन 5 को पार्शियली डिफरेंशिएट करना है y के रिस्पेक्ट में, वेरिएबल y के रिस्पेक्ट में, बोथ साइड्स में. सो डिफरेंशिएटिंग टेम्परेचर, एब्सोल्यूट टेम्परेचर कैपिटल T with respect to the variable y, keeping x constant. So it is del T upon del y, but at constant x. जब y t को y के रिस्पेक्ट में पार्शियली डिफरेंशिएट किया जा रहा है तो x को कांस्टेंट रखना होगा. सो हमने x को कांस्टेंट रखा है, जिसे इंडिकेट करने के लिए ब्रैकेट देकर सफिक्स में x को लिखा गया है. सो डेल t अपॉन डेल y इंटू एक्स मल्टीप्लाइड बाई, सेकेंड टर्म कांस्टेंट होगा इसमें, फर्स्ट टर्म ये इक्वेशन 5 के RHS का फर्स्ट टर्म में, यूजिंग द रूल ऑफ डिफरेंशिएशन ऑफ प्रोडक्ट ऑफ टू वेरिएबल्स. So del s upon del x at constant y plus, now keeping t as constant, it is t multiplied by, now del upon del y of del s upon del x at constant y. So differentiating now del s upon del x at constant y with respect to y, we have del square x into del y into del x minus Now second term is P multiplied by del V upon del X into at constant Y. So differentiating first, it is also the product of two, that is product of differentiation of two variables. So first term is P and second term is del V upon del X at constant Y, and we have to differentiate it with respect to Y. So first of all, differentiating P with respect to Y, we have del P upon del Y at constant X multiplied by second term constant होगा del V. Now second term is constant, del V upon del X at constant Y plus. Now second term is plus, but minus is before the second term of 5, so it is plus minus माइनस होगा. डिफरेंशिएशन में सेकेंड टर्म प्रोडक्ट ऑफ डिफरेंशिएशन ऑफ टू वेरिएबल में बीच में प्लस साइन का यूज होता है, लेकिन चूंकि माइनस पहले है प्रेजेंट इक्वेशन 5 के सेकेंड टर्म में, सो इट इज प्लस माइनस माइनस, सो इट इज माइनस प्लस माइनस माइनस. नाउ कीपिंग पी एज कांस्टेंट, सो इट इज पी मल्टीप्लाइड बाई नाउ पार्शियल डिफरेंशिएशन ऑफ del v upon del x with respect to y, we have del upon del y of del v upon del x is del into del of del v is del square v upon del y with respect to y. डिफरेंशिएशन हमें पार्शियली with respect to y करना है, so it is del y into del x, and which we have obtained from equation number 5, that is differentiating equation 5 partially with respect to y, and it is equation number, suppose it is equation number 5a. Now we have to differentiate the next equation, that is equation number 6 with respect to variable with respect to the variable x, because in LHS it is del u upon del y at constant x. So we have to differentiate both sides of equation 6 with respect to variable x. So write down now differentiating both sides of equation 6 partially with respect to x. We have in the first term we have to differentiate that is first term of LHS of equation 6 is del u upon del y at x. Now differentiating it with respect to x, we have del upon del x of del u upon del y at constant x, that is del square u. In LHS we have del square u upon del x into del y, and in RHS first term is t multiplied by del s upon del y at constant x, that is again the differentiation of product of two variables. So first of all we have to differentiate t partially. We have to differentiate t partially with respect to x. We have del t upon del x at constant y multiplied by, अब सेकेंड टर्म कांस्टेंट होगा इसमें, multiplied by del s upon del y at constant x minus plus second term is now plus keeping t constant, so it is t multiplied by now differentiation of second function del s upon del y at constant x with respect to, we have to differentiate it partially with respect to x. We have del of del x of del s upon del y at constant x is del square s upon del x into del y. So it is del square s upon del x into del y. Now we have to differentiate the second term of equation 6, that is p multiplied by del v upon del y at constant x with respect to x. So again we have first term is we have to differentiate p with respect to x. So it is plus, first term is del p upon del x at constant y multiplied by, second term is remains constant, del v, which is del v upon del y at constant x, and now second term will be positive in the next step, plus now keeping p as constant and differentiating del v upon del y with respect to x. But minus is before this second term of equation 6. So we have plus minus minus. So the next term is माइनस प्लस माइनस माइनस प्लस होगा, लेकिन माइनस आगे में प्रेजेंट है इसलिए माइनस. नाउ कीपिंग p, that is first term of LHS of equation 6 as constant by using the differentiation rule of differentiation of product of two variables. So p remains constant in the next term, so it is minus p multiplied by, now differentiating second term del v upon del y at constant x with respect to x. So it is differentiating, it is del upon del x of del v upon del y. So it is del square, del into del upon del x of del v upon del y is del square v upon del x into del y, and say it is obtained from equation 6. So it is, say it is equation number 6a. Since du is a perfect differential, so we can write, we can equate both sides of equations 5a and 6a, that is del square u upon del y del x equals to del square u upon del x into del y. Since du, that is change in internal energy of the system, is a perfect differential, so we can write del square u equals to del y upon del x, del square u upon del y upon del x equals to del square u upon del x into del y. Similarly, ds is also a perfect differential, so we can write del square x upon del y del x equals to del square x del x into del y, and dv is also a perfect differential, so we can write del square v upon del y into del x equals to del square v upon del x into del y. So now differentiating as du is a perfect differential, so we can equate LHS of both equations 5a and 6a, and so we have del square y as du is a perfect, write down, perfect differential, hence we can write del square u upon del y into del x, which is LHS of equation 5a, and it will equal to LHS of equation 6a. So del square u upon del x del y. So we have del square u upon del y into del x equals to del square u upon del x into del y. Now substituting the values of del square u upon del y into del x in LHS and from equation 5a, and substituting the value of del square u upon del x into del y from equation number 6a. So we can write del t in LHS of in LHS, that is the value of del square u into del square u upon del y into del x is del t upon del y at constant x multiplied by del s upon del x at constant y, and next term of equation 5a is first term is del t upon del y at constant x multiplied by del x, del s upon del x, del s upon del x at constant y. This is the first term. And second term is plus t multiplied by del square s into del y upon del x. So it is plus t multiplied by plus t, it is second term is plus t multiplied by del square s upon del y into del x. Now the third term is minus negative. It was negative, equation 5a. So it is del p upon del y at constant x into del v upon del x at constant y. Third term is minus del p upon del y at constant x multiplied by next term is multiplied by del v upon del x at constant y. At constant y, del v, it was del v upon del x at constant y minus p multiplied by del square v upon del y into del x. So it is LHS of it is the value of del square y, del square u upon del y into del x from equation 6a, equation 5a. And since du is a perfect differential, so del square u upon del x, del y into del x equals to del square u upon del x up into del y. So the value of del square u upon del x into del y is present in LHS of equation 6. So the value of del square u upon del x into del y, we can write RHS of equation number 6a. So we have is equal to, this is the value of LHS, this is the value of del square u upon del y into del x from equation 5a, and from equation 6a the value of del square u upon del x into del y is present here in form of equation 6a. So it is equal to, we have to write del square u upon del x into del y is equal to del t upon del x at constant y multiplied by del s upon del y at constant x plus t multiplied by del square x, del square s multiplied by del square s upon del x into del y, and next term is plus del p upon del x at constant y multiplied by del v upon del y at constant x. It is the third term. It is the third term, that is del p upon del x into y multiplied by del v upon del y at constant x, but this term is negative. So using minus sign here, third term is negative. So there is correction in 6a, third term is negative. In place of plus, we should write here minus. And last term is also negative, so it is minus p. Last term of equation 6a is p minus p multiplied by del square v upon del x into del y. As dx is also a perfect differential, so we can write del square x upon del y into del x is equal to del square s upon del x into del y. So it will cancel out, both terms will cancel out in LHS and RHS of the equation we have obtained. And similarly dv, that is change in volume, is also a perfect differential. So it is so p multiplied by del square v upon del y into del x will cancel out by the last term which is last term of RHS of this equation. So p which is minus p multiplied by del square v upon del x into del y, that is interchange of x and y in the denominator. So this term will also cancel out. So this equation, that is say it is equation number 7. It is equation number 7, in which cancellations are used. So equation 7 becomes, अब कैंसिलेशन के बाद इक्वेशन 7 रिड्यूस हो गया. अब सेकेंड इक्वेशन 7 का फॉर्म होगा. हेंस राइट डाउन इक्वेशन 7 reduces to first term of equation 7 is del t upon del y at constant x multiplied by del s upon del x at constant y minus del p upon del y. Now we have hence equation 7 reduces to del t upon del x at del t upon del y. First term of equation 7 is del t upon del y at constant x multiplied by del s upon del x at constant y, and the second term is now negative of equation 7. We will obtain is negative minus del p upon del y at constant x multiplied by del v upon del x at constant y equals to, now RHS of equation 7 becomes now del t upon del x at constant y multiplied by del s upon del y at constant x, and the next term, that is second term of equation 7, is now minus, after cancellation, is del p upon del x at constant y multiplied by second term is that is product is del v upon del y at constant x, and this equation, suppose it is equation number 8, which is the general equation. It is the general relation. It is the general Maxwell thermodynamical relation. So equation 8 is the general form of Maxwell thermodynamic relation. So write down equation 8. This is equation 8 is, this is the general form of Maxwell's thermodynamical relation. So we have already obtained the general form of Maxwell's thermodynamic relation, but we have to obtain 4 Maxwell's thermodynamical relation using this relation, that is using the general relation. But this relation is the base of all 4 Maxwell's thermodynamical relation. यह बेस इक्वेशन है. इसके हेल्प से हम मैक्सवेल के 4 थर्मोडायनामिकल रिलेशंस को ऑब्टेन कर सकते हैं. टू ऑब्टेन Maxwell's 4 thermodynamical relations, we have to form the set of 4 variables. That is 4 sets. Sorry, we have to use 4 sets of 2 variables each. That is 4 sets of 2 variables. We can use first variable. First set is entropy S in place of x. and second second quantity is volume. So SV is the first set, TV, temperature and volume, is the second set, entropy and pressure, that is SP, third set of two variables, and followed by, that is fourth set of two variables, is we can use temperature in place of X, and in place of Y we can use pressure. So four possible sets, four sets of possible variables, that is four sets of possible variables are four sets of possible variables. Now four sets of possible variables are, first set is SV, that is entropy and volume. Second set is temperature T and volume. Third set is entropy S and pressure P, and fourth set is temperature and pressure. Third set is entropy S and pressure P, and fourth set is temperature T and pressure P. Temperature T and pressure P. These are four possible sets of two variables each, that is SV, that is entropy and volume. Second set is temperature and volume. Third set is entropy and pressure, and fourth set is temperature and pressure. Now we have to obtain Maxwell first thermodynamic relation. अब मैक्सवेल का फर्स्ट थर्मोडायनामिकल रिलेशन के लिए हम यूज करेंगे टू सेट्स ऑफ दैट इज फर्स्ट सेट ऑफ टू वेरिएबल्स, इंट्रोपी एंड वॉल्यूम भी. सो फॉर द फर्स्ट रिलेशन, फॉर द मैक्सवेल्स फर्स्ट रिलेशन, मैक्सवेल्स फर्स्ट thermodynamical relation, which we will obtain from the general form of Maxwell thermodynamical relation given by equation 8, still on the board. So for Maxwell's first thermodynamical relation, we have the first set of two variables SV. So let x is equal to, variable x is equal to S, entropy S, and y is equal to V in relation 8. That is general form of equation. So let x is equal to S, entropy S, and variable y, second variable is y is equal to volume V. Let S is equal to x, let x is equal to S, entropy, first variable x. We have already taken two variables x and y in Maxwell in this derivation, that is the derivation of Maxwell for thermodynamical relations. So x is suppose x is equal to S, that is entropy, and other variable y is volume V. So we can write del S upon del x, differentiating S, entropy S with respect to x. Del S upon del x is del S upon del x, keeping y constant, is hence we have del S upon del x. अब इंट्रोपी एस को एस के रिस्पेक्ट में पार्शियली डिफ्रेंशिएट करेंगे, कीपिंग वाई कांस्टेंट. तो ये क्या हो जाएगा, डेल एस अपॉन डेल एक्स इक्वल्स टू डेल अपॉन डेल एक्स ऑफ एक्स, दैट इज 1, एंड डेल भी अपॉन सिमिलरली डिफ्रेंशिएटिंग भी वॉल्यूम भी विथ रिस्पेक्ट टू वाई, keeping x constant. So del v upon del y at constant x equals to del upon del y of y in LHS. So it is equal to 1, and del s upon del y at constant x is equal to 0. अब s का पार्शियल डिफ्रेंशिएशन करेंगे y के रिस्पेक्ट में. सपोज हमने किया है x इक्वल टू x, सो डेल एस अपॉन डेल y इक्वल्स टू 0 एट कॉन्स्टेंट x 0, एंड डेल v अपॉन डेल x एट कॉन्स्टेंट y इक्वल्स टू 0, because we have taken y is equal to v. So del v upon del y, v को y के रेस्पेक्ट में पार्शियली डिफरेंशिएट करने पर हमें 1 ऑब्टेन होगा एट कांस्टेंट x, बट v को x के रेस्पेक्ट में डिफरेंशिएट करने पर 0 होगा एट कांस्टेंट y. क्योंकि y फंक्शन है, y इज द फंक्शन ऑफ y is equal to v. We have taken y is equal to v. So del v upon del x at constant y will be equal to 0, but del v upon del y is equal to 1. Now substituting these values in equation 8, which is the general form of Maxwell's thermodynamical relation. So del v in place of del s upon del y, first term of relation 8 is del s in place of del s upon del x at constant y, we have it is equal to 1. So first term becomes del t, hence equation 8 becomes, that is general form of Maxwell's thermodynamical relation becomes we have del t upon del y at constant x and del s upon del x at constant y, it is equal to 1, we have obtained, minus, so it is equal to 1, so we can write now the second term, del p upon del y at constant x and del v upon del x at constant y is 0. So second term becomes 0. So second term is 0. So the product of two terms is also 0. And in RHS we have del t upon del x at constant y and del s upon del y at constant x is equal to 0. So in RHS of equation 8, that is in general form of Maxwell thermodynamic relation, LHS of first equation is also 0. So it is 0 minus, now second term is del v upon del y at constant x is 1. So we have second term is of relation 8 is del p upon del x at constant y multiplied by del v upon del y at constant x is 1. So it is del p upon del x at constant y multiplied by 1. So the final relation is, in place of y we can write v, and in place of x we can write x. So we will obtain Maxwell's first thermodynamic relation from the general equation 8 is, which is del t upon del y. So in place of y we have taken v. So substituting v for y को हमने सपोज किया था v, y is equal to v, volume of the system, and x is equal to x is equal to s, entropy of the system. So इस रिलेशन में del t upon del y, तो y के जगह रिप्लेस करना होगा v. एट कांस्टेंट x था तो x को एट कांस्टेंट x के बदले x के जगह पर s, that is at constant entropy, and so it is LHS becomes del t upon del v at constant x at constant s entropy minus is equal to, second term is negative, minus del p upon del x, x is replaced by s, so x के बदले में s यूज करना होगा entropy at constant y, so y is equal to v, volume v. So this is the first Maxwell thermodynamic relation, and say it is equation number A, that is Maxwell first thermodynamical relation, which is del t upon del v at constant s is equal to minus del p upon del s at constant volume. So Maxwell first thermodynamic relation is del t upon del v at constant s equals to minus del p upon del s at constant volume, and this is Maxwell's first thermodynamical relation. Now using three other pairs of variables, that is Tv, that is second pair of two variables, is temperature T and volume V. Third pair is Sp, entropy and pressure, and fourth pair is temperature and pressure. We can obtain three other Maxwell thermodynamical relation. Now for the second set, that is to obtain the second form of second Maxwell thermodynamical relation, we have to take the second set of two variables, that is TV, that is let x equals to temperature T and other variable, second variable y is equal to V. So take x to obtain the second Maxwell thermodynamical relation, let, that is a set of two variables T and V, we have to use let x is equal to T and y is equal to V. So we have del T upon del x is equal to 1 and del V upon del y at constant x is equal to 1, but del T upon del y equals to 0 and del V upon del x at constant volume will also equal to 0. So hence equation 8, that is general form of Maxwell thermodynamic relation becomes the final result, we will obtain del S upon del V at constant temperature T equals to del P upon del T at constant volume. So we will obtain del S upon del V at constant temperature T. This is the final relation we can obtain by similar process as we have obtained equation A, that is Maxwell's first thermodynamical relation. So we will obtain del S upon del V at constant temperature is equal to del P upon del T at constant volume V. And suppose it is equation number B, that is Maxwell's second thermodynamical relation, which we can obtain from equation 8, that is general form of Maxwell thermodynamical relation, and by using two sets of by using the set of two variables, first variable x is equal to T temperature and second variable y, in place of y we can use volume of the system. We can obtain del S upon del V at constant temperature equals to del P upon del T at constant volume, and this is Maxwell's second law of this is Maxwell's second thermodynamical relation. Write down, it is Maxwell's second thermodynamical relation, which is del S upon del V at constant temperature T equals to del P upon del T at constant volume V. Now to obtain the third Maxwell's third thermodynamical relation, we have to take the third set of two variables, which is for Maxwell's third thermodynamical relation. We have to take the third set of two variables S and P. So we have the two variables are S and P, that is taking x is equal to variable x is equal to S entropy and y equals to P. Then del S upon del x at constant y is equal to 1 and del P upon del y at constant x is equal to 1, but del S upon del y, that is partial differentiation of entropy S with respect to y at constant x is equal to 0, and del P and also del P upon del x at constant y will also equal to 0, and substituting those values in relation 8, that is in the general form of Maxwell thermodynamical relation, we can obtain the third we can obtain Maxwell third thermodynamical relation, which is del T upon del P at constant x is equal to del V upon del S at constant pressure. So it is in LHS it is del T upon del P at constant S, that is entropy remains constant, because we have taken x is equal to S. So in place of x we can write at constant entropy, and so it is del T upon del P at constant entropy S equals to del V upon del S at constant pressure P. RHS is del V upon del S, that is change of volume V with respect to entropy S, and keeping pressure remains constant. So we have taken the other variable y is equal to P. So keeping pressure at constant remains, keeping pressure at constant. So it is C, equation number 6, C, which is Maxwell's third thermodynamical relation, which we have obtained by using the third set of two variables, x is equal to S, entropy S, and other variable in place of y it is pressure P, and using the general form of Maxwell's thermodynamical relation given by equation 8, we can obtain this relation, equation C, that is del T upon del P at constant entropy S equals to del V upon del S at constant pressure P, and this is Maxwell's third thermodynamical relation. Thermodynamical relation. Now we can obtain the last, that is fourth Maxwell's thermodynamical relation by taking a set of two variables T, temperature T, and pressure P. So for the to obtain Maxwell's fourth thermodynamical relation, we have to take the fourth set of two variables, that is temperature and pressure, that is take x, first variable x equals to T and y is equal to P. Then we have del T upon del x at constant y equals to 1 after differentiating both sides, that is differentiating T with respect to partially with respect to x, keeping y constant, del T upon del x at constant y is equal to 1, and del P upon del y at constant x is equal to 0, and also del T, अब t को y के रिस्पेक्ट में पार्शियली डिफरेंशिएट करेंगे, तो चूंकि x को x इक्वल टू हमने t सपोज किया है, इसलिए t का पार्शियल डिफरेंशिएशन y के रिस्पेक्ट में क्या होगा, 0 हो जाएगा. सो del t अपॉन del y एट कांस्टेंट x इक्वल टू 0 एंड del p अपॉन del x at constant y is also equal to 0. Since we have taken y is equal to second variable y is equal to pressure, so del p partial differentiation of pressure with respect to y, to del p upon del y, del p upon del y at constant pressure, ये तो 1 होगा, sorry, it is not 0, it is 1. del p upon del y at constant x is equal to 1. Since we have taken y is equal to second variable y is equal to pressure, so partial differentiation of p with respect to y keeping x constant is 1, but partial differentiation of p with respect to x, that is del p upon del x at constant y, and it will certainly equal to 0. And substituting these values in equation 8, that is relation 8, Maxwell general form of thermodynamic relation, write down substituting these values in equation 8, that is the general form of Maxwell's thermodynamical relation, we will obtain the final result as del S upon del P at constant temperature, because we have taken x is equal to T. So x को रिप्लेस कर देंगे t के द्वारा एंड y को रिप्लेस कर देंगे, y के जगह पर p यूज किया जाएगा, रिप्लेस किया जाएगा. सो वी हैव द फाइनल रिजल्ट del S अपॉन del P del S upon del P at constant temperature, x is replaced by T, equals to minus del V upon del T and y is replaced by pressure P at constant pressure P, and it is equation number D, which is the final relation, that is Maxwell's fourth thermodynamical relation, which we can obtain from equation 8, that is Maxwell's general form of thermodynamical relation, by using del T upon del X at constant y is equal to 1 and del P upon del Y at constant X is equal to 1 and del T upon del Y at constant X is equal to 0 and del P upon del X at constant Y is equal to 0. We have obtained the final and fourth relation, that is final and fourth Maxwell thermodynamical relation, which is del S upon del P at constant temperature T equals to minus del V upon del T at constant pressure P, and it is Maxwell's fourth thermodynamical relation, which is the final relation. This is Maxwell's fourth thermodynamical relation, and it is given in equation number D. Now this video is completed. We have derived all four form of Maxwell's thermodynamical relations from the general form of Maxwell thermodynamical relation given by equation 8 by taking four sets of two variables. यदि यह वीडियो आप सभी को पसंद आया हो तो इस वीडियो को अधिक से अधिक लाइक करें, दूसरों से अधिक शेयर करें तथा मेरे यूट्यूब चैनल फिजिक्स क्वांटम क्लासेस को अधिक से अधिक सब्सक्राइब करें. थैंक्स ऑल ऑफ यू फॉर वाचिंग माय यूट्यूब चैनल फिजिक्स क्वांटम क्लासेस.